Breaking the wall to unexplored space. How the Rosetta mission achieved mankind's first close encounter with a comet. Andrea Accomazzo, European Space Agency, Darmstadt.
On the 9th of November 1989, I was a cadet of the Italian Air Force Academy in Pozzuoli near Naples. It was difficult to follow news during those early training days.
So good morning everybody. Thanks for this chance. So we are walking through space. We change dimension to what we have just heard. And I want to tell you about the Rosetta mission. We're talking about comets. Why comets are important? Well, comets are objects like this one. This is the comet we are exploring. We have explored, we've reached, we have landed on. Comets are the pristine objects of our solar system. So they are the first bodies that form, or we believe have formed, in our solar system. And by looking at comets, by exploring them, by analyzing them, we understand how our solar system form, our planets form, and in the end, our scientists can also derive a bit how life developed. So these comets are, it's like going to a building place where you go, a building place of a building. You find pieces of tubes, pipes, tiles, bricks. By looking at those, you understand how a building is built, and that's why we fly to comets. These are the building elements of the solar system. So what are we talking about? Well, these objects, there are billions of comets in our solar system. They're actually at the borders of our solar system. Our solar system, we imagine it as just the planets that we know. Actually, it goes a bit farther out. You see where the Voyager mission is right now, is up there. Well, this is a cloud surrounding our solar system before we reach other solar systems, and there are billions of comets there. Every now and then, these comets hit each other. They come into the inner part of the solar system, and they are trapped there. They fly by next to Saturn, or most likely Jupiter, and these big planets capture these comets inside the solar system. These are the comets we can reach. The outer comets we cannot reach, but we can still reach comets that are trapped in the solar system. And this is what we have done with the Rosetta mission. So it's a long trip to get there. We have spent almost 12 years now in space trying to catch up with this comet. We launched our mission on the 2nd of March 2004 for a 7 billion kilometers trip to reach the comet. It sounds like a very, very large number. Well, all of us here on the Earth, we have already traveled in the same time frame more than 10 billion kilometers. We are traveling through space much faster than what Rosetta had to do when had to go out to the comet. But to get out there, we need energy. Our most powerful rocket couldn't launch us much farther out than what the Earth is around the sun. And the comet is farther out there, so we need to enlarge our orbit much more. How could we do this? Well, we've stolen energy, we've stolen velocity. To whom? To planets. So you have seen in this animation that we flew several times next to planets, and each time we were stealing a bit of the energy of these planets, taking it on board to the spacecraft thanks to gravity. Many people believe we use gravity to launch the spacecraft out. No, no, no. Gravity is just the medium with whom we transfer energy from the planet into the spacecraft. And the spacecraft went out to this orbit, this big orbit now, and finally reached the comet early last year. In August 2014, last year, we finally reached our comet. Does it mean reaching the comet? Well, it's an unknown object. We have to characterize, we have to understand how it works. In spaceflight, one of the most important parameters you need to fly around an object is to know the mass of the object. And this we could speculate on the mass of this specific object. We didn't know exactly the weight of this object. So what we had to do was fly next to the object and use the spacecraft itself. You see in these strange orbits we are flying out there that they are slightly bent. Who's bending them? Well, it's the gravity of the comet. It's pulling the spacecraft to itself. So we were measuring this bending of the trajectory, and we used the spacecraft itself as a sensor, and we could measure that the mass of the comet was 10 billion tons. The comet is not a big object. It's 5 kilometers big. You can imagine like a mountain in the Alps, like the Mont Blanc. The Mont Blanc is 5 kilometers big. This is the comet. It weighs 10 billion tons. With this parameter, then we could design exactly what you are seeing now. We went closer to the comet, we could fly proper orbits around the comet, and we could further characterize the comet itself. What does it mean, characterize? Well, we need an engineering model of the comet. We need a shape model. We need the gravity. We need to know how to fly and need to learn how to fly around the comet. And this is what we had to do in 6 weeks last year. And this is a masterpiece of space flight in terms of flight dynamics, the dynamics that drives and flies the spacecraft around it. Was it enough? No, it was not enough. We wanted to do much more than that. We actually wanted to land on the surface of the comet, grab samples, analyze the surface of the comet itself. So to do that, we had on board the main spacecraft, the mother spacecraft, which is called Rosetta. We had on board a smaller spacecraft, a small probe called Philae. Philae is big. You can imagine as big as a washing machine weighing 100 kilos. So what we did, we were flying around the comet itself, and then one day we shot our spacecraft towards the comet, not on a collision course, but close to it. And you see there now a bit of flight dynamics. What we did there. Philae is a passive body. It was just falling down to the comet the moment Rosetta released it. And it's the point you see there in the circle. What does it mean, a ballistic descent? The precision, the accuracy when landing on the surface of the comet is purely driven by the moment we release Philae, by the position where Rosetta is when Philae was released, and the velocity the spacecraft had. So what we had to control was just to maneuver our main spacecraft. And the last chance we had to maneuver the spacecraft was this turn here. It was a maneuver with the spacecraft. We turned the direction of flight, and then 2 hours later, we just separated Philae. So Philae was falling down for 7 hours. You have to imagine it like this. We have the washing machine, 100 kilos. We are at an altitude above the Mont Blanc of 22 kilometers, and Philae is just falling down for 7 hours. The gravity is very, very weak. We are talking about very, very weak gravity there, falling down for 7 hours. Just give you another number. If we were to make a mistake in the velocity of Rosetta of 1 centimeters per second in controlling it, propagated for 7 hours on the ground is 250 meters error, and this we couldn't afford. We had to do much better than that. So we see our Philae going down, and in the next chart, we will see actually the real images of Philae going down. Before we go to that, I just want to bring back dimension. All these operations were done at 500 million kilometers away from the Earth. It's very difficult to imagine. So I use a couple of tools we typically use in space flight. I need a tennis ball and a chickpea. You can imagine this as our Earth. Our Earth is 12,000 kilometers big, and imagine it as big as this tennis ball. And this is our moon. It's actually a bit bigger than this. And if we scale down the sizes to this, they are separated by 1.5 meters. Now, I cannot demonstrate the rest with my hands. I need the support of a couple of slides. But imagine these two objects are the Earth and the moon. Actually, what we can have is our Earth, our moon. They are separated by 1.5 meters. Now, let's project ourselves to the comet. The comet is 500 million kilometers away. Scale down to this dimension, we're talking about a couple of kilometers. I cannot fly you 2 kilometers away, so we fly the Brandenburger Tor here. So this is where our comet was. Now, we go into the comet itself. It's as big as the Mont Blanc. Imagine the Mont Blanc on this sphere. So this is what the comet is. Imagine one of a very thin human hair, just cut a slice out of it. This is the size of our comet. We had to land the washing machine on top of it, and the washing machine as big as a molecule. So what we have done, we have landed a molecule or a nanowall of a few nanometers onto a slice of a human hair placed on the Brandenburger Tor. From our Earth, this is tennis ball. Actually, all these from Darmstadt. So these are the... What you have seen here in this animation is the descent of Philae seen from Rosetta. So these are images taken from the mother spacecraft of Philae falling down in 7 hours to the comet. And these are the real images taken from Philae in its last minutes going down. If you were a human being, you would see the surface approaching exactly at this velocity. And here you see the altitude. This is 60 meters. It's falling down with 1 meter per second. And I'll let you look at these images now. So this is the last image taken by Philae before landing. It's at 9 meters altitude. So you can imagine you see the surface of the comet from the 3rd floor, a building from the 3rd floor. This is what we are talking about here. Then we went to see where Philae was on the surface of the comet. And this is what we found. We didn't find Philae. We couldn't find Philae. We found a footprint. Come back to this later. But I'm of the opinion that this footprint in the history of spaceflight is comparable to this one. I think will be remembered for a long, long, long time. So what happened to Philae? Well, Philae couldn't anchor on the surface. I said earlier, there is a very, very weak gravity on the surface of the comet. Actually, it's one in the order of the same gravity that is on board the space station. You see astronauts floating in the space station. Well, they suffer the same gravity as Philae was suffering on the surface. So it wanted to anchor on the surface. There were some failures. It bounced on the surface and flew somewhere else. This somewhere else was this sort of cave where he went, but this is just to demonstrate that Philae was alive, actually produced fantastic science in those 3 days. We're still exploiting, of course, the data. This, you see a couple of rocks. This is the leg of the landing gear of Philae. These are rocks surrounding. It's not really a rock. You have to imagine as something extremely porous, and there is ice trap in it. And this is what our scientists want to explore. I want to say as well that the vast majority of the science is not done by Philae itself. Philae was the ground truth for us. But the vast majority of the science is still acquired by the mother spacecraft, Rosetta, that is still orbiting the comet, and will do it for the rest of next year. So this was a breakthrough in space exploration, of course. It's something that nobody has ever done. It was judged extremely challenging by everybody. Even NASA was part of the project in the very beginning. But then they pulled out. They sort of judged the mission far too risky. Well, someone made it. We made it. So what is coming next? Well, in space, this is just a first step, or one of the first steps. We have much more to do in space. You see 3 images on this screen here. Well, we have space debris. We are polluting not only the Earth, we are also polluting space. Space is a resource, and if we are polluting it, we are filling it up with debris, with rubbish, then we are going to not to be able to use this resource anymore. So in the coming decades, this is something we have to tackle in space, absolutely. On the bottom part here, you see an asteroid or a meteorite that flew over the skies of Siberia a couple of years ago. In a bit longer term, maybe we're talking about decades or centuries, our Earth will be threatened by asteroids. No doubt, this will happen. So we have to do something as well for planetary protection. We have to invest in that. We're living nowadays the problem of refugees. They are escaping their own countries because they cannot live there anymore. Where I believe as well that one day, maybe we will have to escape our planet. One day, there will be something either coming from outside, or I would say, if we continue like this, most likely caused by ourselves, that will force us to leave this planet. We're talking about centuries or millennia in this case, but it's something we should start looking at it now. We have to think that one day, maybe we'll have to migrate away, and all these steps in space exploration are just the first steps, the early steps of something we might have to take in the coming years. One last thing, there are no walls out there, and I don't want to be the one that sets up walls. Let's not be the one that sets up walls out there. There's no barriers out there. Let's enjoy space as it is. Thank you very much for your attention.